Longshore drift consists of the transportation of sediments along a coast at an angle to the shoreline, which is dependent on prevailing wind direction, swash and backwash. This process occurs in the littoral zone, and in or close to the surf zone. The process is also known as littoral drift, longshore current or longshore transport. Longshore drift is influenced by numerous aspects of the coastal system, with processes that occur within the surf zone largely influencing the deposition and erosion of sediments. Longshore currents can generate oblique breaking waves which result in longshore transport. Longshore drift can generally be defined in terms of the systems within the surf zone as seen in Figure 1. This figure shows that sediment transport along the shore and surf zone is influenced by the swash, which moves the pebble up the beach at the angle of the waves, and moves the pebble back down the beach due to the influence of gravity. Longshore drift affects numerous sediment sizes as it works in slightly different ways depending on the sediment. Sand is largely affected by the oscillatory force of breaking waves, the motion of sediment due to the impact of breaking waves and bed shear from longshore current. Because shingle beaches are much steeper than sandy ones, plunging breakers are more likely to form, causing the majority of longshore transport to occur in the swash zone, due to a lack of an extended surf zone. Overview: Longshore drift formulas. There are numerous calculations that take into consideration the factors that produce longshore drift. These formulations are: Bezier formula, the Engeland and Hansen formula, the Akers and White formula, the Bailard and Inman formula, the Van Ridge formula, the Watanabe formula. These formulas all provide a different view into the processes that generate longshore drift. The most common factors taken into consideration in these formulas are suspended and bared load transport, waves for example breaking and non-breaking, the shear exerted by waves or the flow associated with waves. Features of shoreline change. Longshore drift plays a large role in the evolution of a shoreline, as if there is a slight change of sediment supply, wind direction, or any other coastal influence, longshore drift can change dramatically, impacting on the formation and evolution of a beach system or profile. These changes do not occur due to one factor within the coastal system. In fact, there are numerous alterations that can occur within the coastal system that may affect the distribution and impact of longshore drift. Some of these are geological changes, for example erosion, backshore changes and emergence of headlands. Change in hydrodynamic forces, for example change in wave diffraction in headland and offshore bank environments. Change to hydrodynamic influences, for example the influence of new tidal inlets and deltas on drift. Alterations of the sediment budget, for example switch of shorelines from drift to swash alignment, exhaustion of sediment sources. The intervention of humans, for example cliff protection, groins, detached breakwaters. The sediment budget. The sediment budget takes into consideration sediment sources and sinks within a system. This sediment can come from any source, with examples of sources and sinks consisting of rivers, lagoons, eroding land sources, artificial sources for example nourishment, artificial sinks for example mining extraction, offshore transport, deposition of sediment on shore, gullies trough the land. This sediment then enters the coastal system and is transported by longshore drift. A good example of the sediment budget and longshore drift working together in the coastal system is inlet ebb tidal shoals, which store sand that has been transported by longshore transport. As well as storing sand, these systems may also transfer or bypass sand into other beach systems, therefore inlet ebb tidal shoal systems provide a good sources and sinks for the sediment budget. Sediment throughout a shoreline profile conforms to the null point hypothesis, where gravitational and hydraulic forces determine the settling velocity of grains in a seaward finning sediment distribution. Longshore occurs in a 90 to 80 degree backwash, so it would be presented as a right angle with the wave line. Natural features. This section consists of features of longshore drift that occur on a coast where longshore drift occurs uninterrupted by man-made structures. Spits. Spits are formed when longshore drift travels past a point where the dominant drift direction and shoreline do not veer in the same direction. As well as dominant drift direction, spits are affected by the strength of wave-driven current, wave angle and the height of incoming waves. Spits are landforms that have two important features, with the first feature being the region at the updrift end or proximal end. The proximal end is constantly attached to land and may form a slight air barrier between the sea and an estuary or lagoon. The second important spit feature is the downdrift end or distal end, which is detached from land and in some cases, may take a complex hook shape or curve, due to the influence of varying wave directions. As an example, the New Brighton Spit in Canterbury, New Zealand, was created by longshore drift of sediment from the Waimakariri River to the north. This spit system is currently in equilibrium but undergoes phases of deposition and erosion. Barriers. Barrier systems are attached to the land at both the proximal and distal end and are generally widest at the downdrift end. These barrier systems may enclose an estuary or lagoon system, like that of Lake Ellesmere enclosed by the Kaitarit Spit or Hapuawa, which form at river coast interface such as at the mouth of the Rākara River. The Kaitarit Spit in Canterbury, New Zealand, is a barrier spit system that has existed below Banks Peninsula for the last 8,000 years. This system has undergone numerous changes and fluctuations due to avulsion of the Waimakariri River, erosion and phases of open marine conditions. The system underwent further changes c. 500 year BP, when longshore drift from the eastern end of the Oaspeta system created the barrier, which has been retained due to ongoing longshore transport. Tidal inlets. The majority of tidal inlets on longshore drift shores accumulate sediment in flood and ebb shoals. Ebb deltas may become stunted on highly exposed shores and in smaller spaces, whereas flood deltas are likely to increase in size when space is available in a bay or lagoon system. Tidal inlets can act as sinks and sources for large amounts of material, which therefore impacts on adjacent parts of the coastline. The structuring of tidal inlets is also important for longshore drift, as if an inlet is unstructured, sediment may bypass the inlet and form bars at the downdrift part of the coast. Although this may also depend on the inlet size, delta morphology, sediment rate and bypassing mechanism. Channel location variance and amount may also influence the impact of longshore drift on a tidal inlet as well. For example, the Arcachon Lagoon is a tidal inlet system in southwest France, which provides large sources and sinks for longshore drift sediments. The impact of longshore drift sediments on this inlet system is highly influenced by the variation in the number of lagoon entrances and the location of these entrances. Any change in these factors can cause severe downdrift erosion or downdrift accretion of large swash bars. Human influences. This section consists of longshore drift features that occur unnaturally and in some cases have been constructed to enhance the effects of longshore drift on the coastline, but in other cases have a negative impact on longshore drift. Groins. Groins are shore protection structures, placed at equal intervals along the coastline in order to stop coastal erosion and generally cross the intertidal zone. Due to this, groin structures are usually used on shores with low net and high annual longshore drift in order to retain the sediments lost in storm surges and further down the coast. There are numerous variations to groin designs, with the three most common designs consisting of zigzag groins, which dissipate the destructive flows that form in wave-induced currents or in breaking waves. T-head groins, which reduce wave height through wave diffraction. A Euro unregistered trademark head, a fishtail groin system. Artificial headlands. Artificial headlands are also shore protection structures, which are created in order to provide a certain amount of protection to beaches or bays. Although the creation of headlands involves accretion of sediments on the updrift side of the headland and moderate erosion of the downdrift end of the headland, this is undertaken in order to design a stabilized system that allows material to accumulate in beaches further along the shore. Artificial headlands can occur due to natural accumulation or also through artificial nourishment. Detached breakwaters. Detached breakwaters are shore protection structures, created to build up sandy material in order to accommodate drawdown in storm conditions. In order to accommodate drawdown in storm conditions, detached breakwaters have no connection to the shoreline, which lets currents and sediment pass between the breakwater and the shore. This then forms a region of reduced wave energy, which encourages the deposition of sand on the lee side of the structure. Detached breakwaters are generally used in the same way as groins, to build up the volume of material between the coast and the breakwater structure in order to accommodate storm surges. Ports and harbors. The creation of ports and harbors throughout the world can seriously impact on the natural course of longshore drift. Not only do ports and harbors pose a threat to longshore drift in the short term, they also pose a threat to shoreline evolution. The major influence the creation of a port or harbor can have on longshore drift is the alteration of sedimentation patterns, which in turn may lead to accretion and/or erosion of a beach or coastal system. As an example, the creation of a port in Timarup, New Zealand in the late 1800s led to a significant change in the longshore drift along the South Canterbury coastline. Instead of longshore drift transporting sediment north up the coast towards the Waimatatā Lagoon, the creation of the port blocked the drift of these sediments and instead caused them to accrete to the south of the port at South Beach in Timarup. The accretion of this sediment to the south, therefore meant a lack of sediment being deposited on the coast near the Waimatatā Lagoon, which led to the loss of the barrier enclosing the lagoon in the 1930s and then shortly after, the loss of the lagoon itself. As with the Waimatatā Lagoon, the Wasdijk Lagoon, which currently lies to the north of the Timarup port, is undergoing erosion and may eventually breach, causing loss of another lagoon environment. References, citations. Books, Brun, P. ed. Port and Coastal Engineering Developments in Science and Technology. South Carolina, P. Brunner, Hart, D.E. Marston, I. Francis, M. Chapter 20, Coastal Systems. In Winterburn, M. Knox, G.A. Marston, I.D. Burrows, C. Natural History of Canterbury. Canterbury University Press 30 pppa 653 Euro 684 Reeve, D. Chadwick, A. Fleming, C. Coastal Engineering Processes, Theory and Design Practice. New York, Spin Presser, Journal Articles, Kirk, R.M. Lauder, G.A. Significant Coastal Lagoon Systems in the South Island, New Zealand. Science for Conservation. DOC 46 pppa 13 Euro 24 Michel, D. Hauer, H.L. Morphodynamic Behavior of a Tidal Inlet System in a Mixed Energy Environment. Physical-Chemical Earth 22 pppa 339 Euro 343 Peterson, D. Diergaard, R. Fraidso, J. Modeling the Morphology of Sandy Spits. Coastal Engineering 55 ppA 671 Euro 684, Soons, J.M. Schulmeister, J. Holt, S. The Holocene Evolution of a Well-Nourished Gravelly Barrier and Lagoon Complex, Carritarret Spit, Canterbury, New Zealand. Marine Geology 26 ppA 69 Euro 90 External links, photos, animation and explanation for schools, geography-site.co.uk, intranet list Junior Hans SCH Lucas. A brief animation on longshore drift. USGS. A Euro coastal erosion on Cape Cod, Woodshoal. USGS Gov, shore drift, ec.wa.gov, longshore drift in South Carolina, cofc.edu.